Welcome to Chapter 26c, Relativity, Events and Measurements. We're also going to talk about simultaneity. And upon successful completion of this, you should be able to describe events and measurements and also simultaneity. Okay, now what is an event? Suppose we have a firecracker that explodes at a specific time and place. This is an example of an event, which has 4 space-time coordinates as measured at any particular reference frame. So for instance, here we have 2 reference frames, S and S prime. S prime is moving to the right with respect to S at velocity v. And in S, we have this event has space-time coordinates x, y, z, and t, where t is time, and different space-time coordinates in frame S prime of x prime, y prime, z prime, and t prime. Now, we had to make measurements somehow, and it's kind of complicated in relativity because there's something called light travel time. In normal events, the light travel time is so small that we don't really have to take it into account. When we talk about relativity, especially over large distances, like astronomical distance, light travel time becomes extremely important. To the nearest star, that's 4.2 outside of the sun, 4.2 light years away. That means it takes light 4.2 years to reach us. That's the light travel time from that star. The sun is 8.5 minutes away. So we don't know what happens on the sun till 8.5 minutes after it happens. That's the light travel time. We have to find some way of taking that into account. So we're going to imagine that a reference frame is filled with a cubic lattice of meter sticks as shown. At every intersection is a clock. All the clocks in the reference frame had to be synchronized or else they're useless. Events are measured relative to these imaginary meter sticks and clocks. So if an event occurs, we measure it. The space-time coordinates of the event are measured by the intersection of the nearest meter sticks and the nearest clock. And all the clocks are synchronized. And this is reference frame S. Now, it's important that all the clocks in the reference frame be synchronized, meaning that all clocks in the reference frame have the same reading at any one instant of time. We begin by setting each clock to display the light travel time, that is d over c, from the origin, where d is the distance from the origin to that clock. But we don't start the clocks yet. So here's the clock at the origin. That one's always set to 0 because it's at the origin. There's no light travel time from the origin to this one. This one is 300 meters away from the origin. The light travel time is 1 microsecond. Light travels 300 meters in 1 microsecond. So the 1 microsecond is the light travel time. So we preset this clock to that light travel time. We do this for every clock. Anything that's like 600 meters away, it would be preset to 2 microseconds. 900 meters away would be preset 3 microseconds ahead. Now, at the origin, at the same time that we start this clock, a light flashes. And the wave front begins traveling out at the speed of light. And it eventually will reach this other clock. And when it reaches this other clock, the photodetector in this clock turns this clock on. And this light wave keeps traveling outward, and eventually all the clocks are turned on. And because they've been preset with their light travel times, so they all read the same time at the same time. And they're all synchronized to the origin clock. Now, simultaneous and light travel time. 2 events, 1 and 2, that take place at different positions, x1 and x2. In other words, x1 is not equal to x2, but at the same time, t1 equals t2, as measured in some reference frame, are said to be simultaneous in that reference frame. Simultaneity is determined by when the events actually happen, not necessarily when they are seen or observed, because the light travel time has to be taken into account. In general, simultaneous events are not seen at the same time because of the difference in light travel times from the event to an experimenter. This is the reason why the light year is used in astronomy. Because in astronomy, everything is far enough away that usually that light takes some appreciable time to reach us from there. So the light year is the distance light travels in 1 year. So if something is 5 light years away, that's the light travel time between it and us. If something is 2 million light years away, it takes like 2 million years to reach us from that object. So for example, you live in a system that is 5 light years from a supernova. The supernova is a violent death of a large star, and it can be seen just about everywhere. It would take 5 years for the light from that blast to reach you. That means you wouldn't know about it for 5 years. And when it finally did reach you, it was 5 years in the past. Your alien friend whose home is in a system 10 light years from the supernova would not see the light from this blast for 10 years from the time of the star's death. The supernova did not occur at different times, but you and your friend would observe it at different times. He would observe it 5 years after you because he's 5 years further away. That is 5 years more light travel time. Even if you could, now you're thinking, I can hear you thinking, you guys with the cell phones, everybody with a cell phone, right? I'm going to call him up and take a picture of the supernova and send it to him. Even if you do that, you call your friend when you see the blast. It would take at least 5 years for your signal, that's the speed of light thing, your signal does not travel faster than the speed of light, to reach him. So he still would not know about the event for at least 10 years after the blast. 5 years to reach you. You send him a picture of the supernova, it's going to take another 5 years for it to reach him. So it still takes 10 years for him to see it. Now, an observer in frame S witnesses an event to occur at time t. The actual event must have occurred at some time period delta t before the event being witnessed. That's that light travel time thing. The time period it takes for the image of the event to reach the eye or sensor is delta t equals delta x over c. That's the light travel time. Delta x is the distance between you and the event. So in the supernova example before, for you, delta x is 5 light years. And since the speed of light is, 1 light year per year, that delta x over c would be 5 years. That's the delta t. Thus, t prime equals t minus delta x over c. This is like the sound of thunder, where you know the origination of the sound occurred before you perceived it because you saw the lightning. Now, for the supernova example, if you observed the supernova in the year 2020 and the victim star is 5 light years away, you would know that the star died in year 2015. So here's when you observe it, that's 2020. Here it's 5 light years away, that's delta x over c. So 2020 minus 5 is 2015. That's when it happened. Your alien friend, he would see the event in 2025. He's 10 light years away, so 2025 minus 10 is 2015. Both you and he, if they use this equation, would agree that the event was simultaneous, that it occurred at the same time. But you wouldn't see it at the same time. You'd see it in 2020, he'd see it in 2025. But if you both use the same equation, know your light travel times, then you're going to agree that it actually occurred in 2015. And that's how that works. Yes, I know it's enough to make your brain bleed. So, but don't panic, all right? A firecracker explodes high overhead. You notice a slight delay between seeing the flash and hearing the boom. At what time did the event firecracker explodes occur? Now, you don't worry about the slight delay between seeing the flash and hearing the boom. That's just due to the fact that sound travels much slower than light. What you're worrying about is that there's a distance between you and the firecracker. There better be, or else it'll do something damage to you. Firecracker explodes overhead. It's at a distance away from you, so it's going to take time for light to travel that distance. So the actual event occurred slightly before you saw the flash. It takes time for the light of the explosion to reach you. In fact, you're seeing everything in the past. It always amuses me when people say live in the present. My response to that as a physicist and an astrophysicist, saying you can't do that. You're asking people to do something impossible because it takes time for light to travel. And you can't know about an event until you see it, until you experience it. And that experience has to do with the speed of light. So the further away something is, the further it is in the past. It takes 3.3 nanoseconds to travel 1 meter for light. When you look at something 2 meters away, you're seeing as it was 6.6 nanoseconds in the past. The sun is 8.5 light minutes away, so you see the sun as it was 8.5 minutes ago. The nearest star other than the sun is 4.2 light years away, so you see it as it was 4.2 years ago. Now, this is the reason we use light travel times in astronomy, because it's so important to us. Everything has a light travel time, because astronomy, the distances are so huge. Okay, are the explosions simultaneous? An experimenter in reference frame S stands at the origin looking in the positive x direction. At time t equals 3 microseconds, she sees firecracker 1 explode at x equals 600 meters. A short time later, at time t equals 5 microseconds, she sees a second firecracker explode at x equals 1200 meters. Are the two explosions simultaneous? And if not, which one exploded first? The physics of this is simultaneous events and relativity. The knowns and unknowns. She says T1 is 3 microseconds at x1 equals 600 meters. T2 is 5 microseconds at x2 is 1200 meters. She needs to know T primes. So we use the equation T prime equals T minus delta x over C. So her first T is 3 microseconds. Her first distance, delta x, is 600 meters. And here's the light speed written for 300 meters per microsecond. Ends up being 1 microsecond. This is when the event actually occurred. she applies the same equation again using T2 and the distance, and she comes out with the same time. This means it actually occurred at the same time. She didn't see them at the same time. She saw this one occurred 3 microseconds, and this one occurred 5 microseconds, but the first one was only 600 meters away. The second one was 1,200 meters away. So when you take the different light travel times into account, they end up having occurred at the same time, so they are simultaneous. Firecrackers A and B are 600 meters apart. Sam is standing halfway between them. Susie is standing 300 meters on the other side of firecracker A, so she's 300 meters away from firecracker A, and she's 900 meters away from firecracker B. Sam sees 2 flashes from the 2 explosions at exactly the same instant. According to Susie, who understands simultaneity, firecracker A explodes before, at the same time, or after. Now, she doesn't see the flashes at the same time, but when you see an event, it's not the same time as when the event occurred. Now, what you want to look at here is Sam sees 2 flashes from the 2 explosions at exactly the same instant, and he is halfway between them. That means he's equidistant. So he's going to see them as happening as events, as simultaneous. So Sam will determine that these events are simultaneous because the light travel time to both of them are the same, and he saw them at the same time. Now, Susie knows simultaneous, and if she knows her distances and times, she can use the formula T prime equals T minus delta X over C to determine the true event, the actual time that they occurred. When she applies this formula, she's going to see that the times are simultaneous. She won't see the flashes at the same time because she's further away from firecracker B than she is from firecracker A. But if she applies the formula correctly, measures the time correctly, and knows the distances, she will find out that T prime A equals T prime B, and then she will know that they're simultaneous. Okay, so the relativity of simultaneity. Hard to say that fast. Here we have a railroad car. It's traveling to the right with a velocity v. Peggy stands in the middle of the railroad car. There are 2 firecrackers on the ends of the railroad car, and she has a light detector. The firecrackers, when they explode, do 2 things. They explode with a bright flash, and they also leave a burn mark on the ground. Ryan, at this instant, is equidistant from the ends of the car, so Peggy's passing him at this instant. Okay, so the firecrackers tied to each end of the car just above the ground. The firecrackers explode with bright flashes at the instant shown in the figure when they're equidistant from Ryan. They mark the ground with burn marks, so Ryan knows exactly where their positions are. The 2 events, because this distance is the same as that distance, and Ryan sees them exactly at the same time, the 2 events are then simultaneous in Ryan's reference frame, because he can determine that the light travel times are the same. He saw them at the same time, so T prime right is going to be the same as T prime left. So he will say that these events are simultaneous. So here's the sequence of event in Ryan's reference frame. Here's the instant when the firecrackers explode, and the burn marks are equal distance from Ryan, and he can determine that they are simultaneous. This is a little bit later, and the car is moved to the right. It's moving to the right with velocity v. This is the burn marks on the ground right here, these 2 dots here. Here is the wavefront of the light that's coming from each one of these firecrackers. Now, Peggy hasn't seen either one yet, but the car is still moving here. So she's moving into this wavefront. She's going to see the right-hand one before she's going to see the left-hand one. Now, at this point, the car has moved a little further. At this point, the waves have reached Ryan simultaneously, and they have traveled equal distances, so he's going to agree that they're simultaneous. His T primes are going to be the same, right and left. Peggy has detected the right-hand one because this wavefront has passed her. She has not yet seen the left-hand one. So here's what Peggy sees. To her, the right-hand firecracker occurs first because she's traveling into this wavefront. So she's effectively shortened this distance here. She's going to see this one occur first. She has not yet seen this one. The sequence of events in Peggy's reference frames are here. The 2 events are not simultaneous in Peggy's reference frame. She would see them happen at different times. She could use the distances and light travel times to determine the true sequence of events and that they are simultaneous. The 2 events are simultaneous in Ryan's reference frames. He would see them happen at the same time. If he used the distances and light travel times, he would find that the events occurred at the same time. This is called the relativity of simultaneity. So Peggy would see them happen at different times, but she could use the distances and light travel times to determine the true sequence of events and determine that they were really simultaneous. Yes, I know this stuff makes your head hurt. Peggy is standing at the center of a railroad car as it passes Ryan. Firecrackers A and B at the ends of the car explode not necessarily at the same time. A short time later, flashes from the two explosions reach Peggy at the same instant. In Peggy's reference frame, firecracker A explodes before at the same time as after firecracker B. They will explode at the same time because she's equidistant from the two firecrackers and she sees them happen at the same instant. That's in Peggy's reference frame. Peggy's standing at the center of a railroad car as it passes Ryan. Firecrackers A and B at the ends of the car explode not necessarily at the same time. A short time later, flashes from the two explosions reach Peggy at the same instant. In Ryan's reference frame, firecracker A explodes before at the same time or after firecracker B. Okay, now Ryan has to agree that the flashes reach Peggy simultaneously because their arrivals could be measured with detectors, and he knows that she is equidistant from the two firecrackers. In Ryan's frame, Peggy is moving away from A and toward B. So this means firecracker A had to explode first if the light waves from A are to reach Peggy at the same instant as the light waves from B. So this one had to explode first because it had a further distance to reach to get to Peggy. Thank you.